Yes, hello, fine dear students. Today we are going to discuss about the mechanical properties of solids. Mechanical properties of solids we are going to discuss. So in that, today first what we are going to discuss here means we are going to discuss about the elastic properties. Elastic properties. So what is meant by elastic properties which we are going to learn here? So in that basically what is meant by elastic properties means what is meant by elasticity basically we have to know. What is meant by elasticity? Tendency of material to regain its original shape and size is called elasticity. Tendency of material to regain its original shape and size is called elasticity. In this we are having parts here. How many types is there means basically three types is there here. So what are those three types means we can take like this. First one, second one, third one which you can take here. So the first type what we are having perfectly elastic. Next partially elastic. Third one perfectly plastic which we can call it as perfectly plastic materials. So here what is meant by perfectly elastic means it is a property of material which regains shape and size completely. It is a property of the material which it regains shape and size completely, which you can call it as. Next, what is meant by partially elastic? We have to know here. What is meant by partially elastic? It is a property of the material which it regains shape and size partially, which you can mention. Property of material which it regains shape and size partially is called what? Partially elastic, we can call this. Next, what we need to discuss about? We need to discuss about the perfectly plastic. What is mean by perfectly plastic means? Property of the material. Property of material which it does not regains its shape and size completely is called what we can call it as perfectly plastic. You can tell perfectly elastic means completely regains shape and size. Partially regains shape and size is called partially elastic. Perfectly plastic means what we can tell here, which it does not regains its shape and size completely is called what we can tell it as. We can tell it as perfectly plastic, which we can tell here. Now we are going to discuss about what is meant by stress. We are going to discuss here. What is meant by stress? So what is meant by stress here means we can define like this: the internal restoring force the internal restoring force developed per unit area. Developed per unit area of deforming body is called stress. So generally, if you take any body here like this, one solid rod we are having here, which is having length L here. Now what we are doing here, we are applying force on it. If we apply force on it, what will happen? Elongation will come. So elongation due to what will come? Due to applied force. Due to internal molecules, what will happen? Again, this rod tries to come back. For example, best example I'll take here. We are having one spring like this here, who is having constant K. This is initial level. If I connect load to this, what will happen? We'll get elongate like this, right? Elongate like this. Due to what? Due to load mg. So if I remove mass here, what will happen? The spring will go back. Due to what it will go back? You applied force or internal forces means in the spring, if you observe here, no, these each molecules are going away when you applied load. So if you remove the load, no, what will happen? These both molecules are coming together. Due to what they are coming together here? Due to restoring forces. This force is called what? Restoring force. The force which is developed inside the body due to applied forces is called restoring force, which we can explain here. Okay. Now stress can be written as what here means applied force upon this area is called what here? Stress we can define here. So stress equal to what we can write here? Applied force upon, restoring force upon unit area, which we can mention here, F by A. So where A is nothing but what we can tell here, cross-sectional area. Cross-sectional area, which we can define here. So what is SI unit? If you want to write it means SI unit. Force upon area, right? Newton per meter square, we can write it. What is CGS unit? CGS unit can be written as what? Newton can be written as dyne, right? Dyne per centimeter square, we can write it. We need to mention the dimensional formula. How to mention dimensional formula? You can write m power 1, L power 1, T power minus 2 divided by meter square. That's nothing but length power 2. One length will get cancelled. Means finally dimensional formula comes out to be what? Dimensional formula equals to m power 1, L power minus 1, T power minus 2. And this Newton per meter square also can be called as sometimes Pascals, which we can call it as. Pascals, which we can call it as. And this fellow can be called as what here? Poise, we can call it as. And we know that 1 Pascal equal to how much will get it? 1 Pascal equal to 10 poise will get it here. So this is how you can convert into SI units to CGS units. 1 Pascal equal to how many poise will get it? 10 poise, which we can discuss here. Now we are going to discuss how different types of the stress we are going to discuss here. How many types of stress is there we are going to discuss here? Stress. So stress is basically divided into 3 types actually. First one, what we can call it as means here, normal stress, or this is also called as longitudinal stress. Second one, we can call it as shear stress, or we can call it as tangential stress. Third one, we can call it as volumic stress, or this also can be called as what? Compressive stress. Simply I can call it as this is as one-dimensional, this is as two-dimensional, this is three-dimensional stress, which we can define here. So in normal stress or longitudinal stress, what we are having means we are having one wall like this. To this we fixed a rod here, we hinged a rod here. On this rod, what we are going to apply here? We are going to apply force here. An application of force, what will happen means elongation will come here. How much elongation is coming? Let us assume delta L is their elongation. So how can you define here? Stress means nothing but stress equal to force upon normal area. Otherwise normal force upon cross-sectional area, which you can define here. Normal force means this is the force which you applied perpendicular to the cross-sectional area is called what? Normal force, which you can define. So stress equal to force upon perpendicular area, which you can write it here. Next, we need to discuss about the shear stress or tangential stress. What is meant by shear stress or tangential stress means we're having one plane surface here like this. To this, what we're having means we're having one body like this. And this bottom part is fixed actually. This part is fixed to the plane. Fixed here. Now what we are going to do here means we are going to apply the force on this body. So how you are applying? Tangentially on one end you applied force here. If you apply force here, what will happen here? On the top end, deformation will come like this. And I'm assuming this angle is theta, it's got deformation. And the side length, how much is there means L is there here. How much it got deform means X we are going to choose here. X or delta L, anything we are going to choose here. So stress can be written as what here means stress equal to F upon A, we can write it here. But here F is called what means tangential force, which we have to define here. Tangential force. Next, what we need to discuss here, we need to discuss about the compressive stress or volumic stress. This also can be called as hydraulic stress. Hydraulic stress. Also, we can call it as. So generally, what we are taking means we are taking one air or water. Let it use. Hydro means water, right? Water we are choosing here. So in this, what will happen means when body is there here, due to water molecules and this, what is going to apply means force is going to apply. In this direction, what is going to apply? Force is going to apply. So what will happen as a result? So stress is developed on this body due to that water molecules. So what we can define here, stress equal to what we can write means force upon unit area, we can define here. So where area is nothing but area should be perpendicular to the force. You can observe area everywhere. So area is perpendicular to the force. Area is perpendicular to the force. Area is perpendicular to the force. This type of forces which you have to take into consideration. So basically three types of stress is one is normal stress, longitudinal stress, shear stress, tangential stress, volumic or compressive or hydraulic, anything we can take. So normal stress means what? Longitudinal stress, sorry. Normal force upon perpendicular area, tangential force upon area. So compressive stress means force upon area, that force and area should be perpendicular to this. And hydraulic means what? Water, we are taking one example, that's why we can mention this also like hydraulic, which we can mention here. Hydraulic. Now we're going to discuss what is the differences between stress and strain. We're going to discuss here. Stress and strain. Strain not. First, let me discuss about pressure, then we will discuss about the strain. Pressure. See, how can we define stress means we can define like stress is nothing but force upon area, but that force is what here? So stress equal to force upon area, but that force is what here? Restoring force. Restoring force. But here pressure, what we are having here? Pressure equal to force upon area. This force can be just applied force. F equal to what we can write here? Applied force upon unit area. Applied force. Here stress is nothing but tensor quantity. Tensor quantity. And pressure is nothing but scalar quantity. Scalar quantity. Here we have to know what is meant by tensor quantity. We have to know here. Tensor quantity. So what is meant by tensor quantity means the quantity which has direction but it does not follows Vector addition rules. Vector addition rules. Examples like we can take like stress, moment of inertia, MOI, and electric current. These are the examples. These all having directions and it does not follow vector addition rules here. For example, let me take here, current, let me take one example and to explain you. We are having two wires like this. Through this 3 amperes is going, through this 4 amperes current is going. How much current should go here is the question here actually. So how much current is passing means we can tell simply here, this is 3, this is 4 means we can tell 7 amperes. But if you follow vector addition rules, no, 3 amperes is this one vector and 4 amperes is this one vector here. Angle between these two is how much? 90. So if you apply parallelogram law of vectors, no, so current net equal to what we'll get it here, under root of 3 square plus 4 square plus 2 into 3 into 4 into what we can get it here, cos 90. Cos 90 is how much? 0. So under root of 3 square plus 4 square. So it's nothing but what we'll get it? 5. But 5 amperes we're getting. But answer is how much here? 7 amperes we got it. So that's why. So the quantity which has direction, but it does not follow what? Vector addition rules is called what we can tell as tensor quantity. So examples are said stress, moment of inertia, and electric current we can tell here. But here while here pressure is nothing but which quantity here? Pressure is nothing but scalar quantity we have to know. We know here. And what is meant by strain we have to define here. Strain basically how can you define means simply we can write like delta L by L we can write it here. What is meant by delta L by L means change in length by original length. Original length which we can call it as, it does not have any dimensions. Length upon length will get cancelled, no? So it is dimensionless quantity which we can tell here. So strain can be called as what here? Change in length upon original length simply which we can define here. Now we are going to study different types of strains here. We are going to study different types of strain. So we are having like this. First one, what we are having means here we are having tensile strain or longitudinal strain. Tensile strain, or this also can be called as what? Longitudinal. Longitudinal strain. Here we are having here shear strain, or this also can be called as what here? Tangential strain. One more is called what we can call it as means bulk strain, or this also can be called as what we can call it as volumic. Earlier we discussed in stress, no, similar way. This is one dimensional, this is about 2 dimensional, this is about 3 dimensional, which we are going to discuss here. So what is meant by tensile strain means here we are having one body which is having original length L. I applied force here. Due to application of force, what will happen means that is elongated like this. So how much elongation come into picture means delta L elongation is come into picture. So that's why here strain can be written as what means strain equal to change in length upon original length, which you can write it here. Change in length upon original length, no dimensions, no SI units, which you can mention clearly here. Now we need to discuss about the shear strain. What do you mean by shear strain? We are having one body here we discussed. In this body, we place one body here. And this bottom part is fixed, I told you, fixed. Now what we are going to do here, we are going to apply some force on this end. Tangential force we are going to apply here. If you apply, what will happen here? Deformation will come into picture. In top end, we will get like this deformation. This length is how much we know? Length is L. How much deformation is coming here? X distance deformation is coming here, theta. We need to calculate this theta here. So that is called what we can call it as strain here. Therefore, strain equal to what we can write it here? That's nothing but theta, tangential strain, that equal to, so it's almost look like arc, this part. So theta can be written as what here? Arc length upon radius, na? So x upon L we can write it here. So that is nothing but which strain? Tangential strain, which we can discuss here. Next, bulk strain we are having. So bulk strain, earlier bulk stress what we discussed here, we are having one body here, so which is placed in water. So what will happen means here in all directions force is going to apply. Like this force is we are going to apply. If force is going to apply means what will happen? As a result, that body shape will come like this. Means what will happen? Volume is decreasing or increasing means volume is decreasing. That's why we can write here strain equal to what we can write it here. Change in volume upon original volume we can write it. But here I'm giving one negative sign. So why? Because for this case, this particular case, volume is decreasing, which we take an example. That's why we can write it here. Strain equal to what we can write it here? Minus delta V by V, which we know here. So first one is called what here? Tensile strain or longitudinal strain. So that's nothing but change in length upon original length. Second one is called what? Shear strain or tangential strain here. So if you apply force in this corner, what will happen? You will get deformation. So how much deformation it will measure is nothing but shear strain. We can call it as strain equal to x by L. Theta equals to arc length upon radius, which you can write it. Arc length is x, radius is nothing but L. Next, we are going to discuss about the bulk strain or volume strain. So what we can write here, bulk strain can be written as what here means. So we are applying force in this all directions. As a result, what will happen? Volume will be going to decrease. So change in volume upon original volume. But why we given negative sign here means for this particular case, volume is going to decrease. That's why we are going to discuss what we are going to discuss here. Volume is decreasing, minus we are going to keep here. Now we are going to discuss about the Hooke's law. We are going to discuss here. Hooke's law. What is meant by Hooke's law means within elastic limits, stress is directly proportional to strain here. So what does this law will tell? Stress is directly proportional to strain. Directly proportional to strain. So if you remove proportionality, you will get a constant. Therefore, stress equal to some constant into strain, which we can write it here. So stress by strain can be written as what here? Stress upon strain can be written as what here means? One constant will get it, right? This constant is called what means? Modulus of rigidity. Sorry, modulus of elasticity. Or elastic moduli also we can call it as. Therefore, this symbol is generally what we can give means E here. E can be written as what here? Stress upon strain. So this can be called as what here? Modulus of elasticity, which you can call it as here. Modulus of elasticity. And what is meant by modulus of elasticity? The ratio of stress to the strain which is called modulus of elasticity. Within elastic limits, stress is directly proportional to strain. Stress is directly proportional to strain means if you remove proportionality here, we'll get a constant. Since strain here, so stress by strain equal to what we get it? Constant. That is called modulus of elasticity. So that symbol is generally what we can give E. E equal to stress by strain. That is called modulus of elasticity, which we can tell here. So in this slide, we are going to discuss types of elasticity of moduli. We are going to discuss here. Actually, again, this is also how many types is it? 3 types is there here. First one, what we can call it as one dimensional. Second one, what we can call it as two dimensionals about area. Third one, we can call it as about volume, which we can define here. So first one is called what here basically? First one is called Young's modulus. Young's modulus. And symbol is Y, which we can give here. Second one is called shear modulus or rigidity, which we can call it as rigidity. Symbol is given by eta. And third one is called bulk modulus. Symbol is given as B. Bulk modulus. So generally, what is meant by Young's modulus means what we can call it as means Young's modulus equal to longitudinal stress upon longitudinal strain. Longitudinal stress upon longitudinal strain. So Young's modulus can be written as what we can write it here. Longitudinal stress, that's nothing but F by A divided by longitudinal strain. Strain can be written as what here? Delta L upon L. So what will happen as a result? We can write like this. F by A into delta L by L. This is a very important formula where you will get all the NEET, CET, JEE numericals will get almost all based on this formula only. Next, what we are going to discuss here, shear modulus or rigidity modulus. This can be written as what here? Y equal to shear strain upon shear stress upon shear strain. Shear stress is nothing but what we know, F by A. That's nothing but theta. Therefore, eta, right? Sorry, eta equal to. So F by A upon theta value is how much here? X by L. So if we rewrite here, no, eta equal to what will get it here? F by A into X by L, which will get it here. This is called what we got it here? Rigidity modulus, which we got it here. Next, we are going to discuss about the bulk modulus. Bulk modulus is nothing but bulk stress upon bulk strain. Bulk modulus equal to what we can write? Bulk stress upon bulk strain. That's nothing but F by A upon what we can write it here? Minus delta V by V. This F by A can be written as what here means? Pressure, we can write it here. So what we can write it here means pressure upon delta V by V. Why we given negative sign means which we choose, and in that case we got negative sign there. So that's why we're keeping here. According to case, we are going to write that negative sign where the volume is expansion or volume is getting decreased. We need to take here. Now we're having some relations between y, rho, and sigma, these all things. So first, let me discuss once again these things, then we'll discuss it. One dimensional, two dimension, three dimensions, Young's modulus, shear rigidity, or bulk modulus. So Young's modulus is called what we call it as longitudinal stress upon longitudinal strain, shear stress upon shear strain, volume stress upon volume strain, or bulk stress upon bulk strain, which we can call this F by A delta L by L. So F by A L into delta L. So eta equal to what we can write F by A divided by theta, F by A into X by L. It will come to numerator. In this case, F by A we are going to write here pressure. So this is the same formula which we are going to use in. So where we used it means we are using thermodynamics. Again, same formula which we used in waves chapter also to find the sound waves Laplace correction or Newton's formula. So we are going to take help of the here bulk modulus only, which we are going to take here. See, fine, in this slide, what we are going to discuss means we are going to discuss about the Poissons ratio. We are going to discuss here. So what we are doing means here we are taking one body here, one cylinder. Here one support is there. So this support what we hanging here means one big cylinder is hanging like this cylinder. So the cylinder length is how much? L I am going to take here. This fellow radius how much I am taking means R I am going to take here. So what will happen due to weight downward? What will come generally here? Weight of the cylinder will come, right? Mg. Due to that weight, elongation will come into picture here. So when elongation is coming now here, what will happen here? So this will become like this. It's going to become like this. Now what will happen here? Its length going to become increased, right? So let me take new length is nothing but how much we can take here means this much length it is increased here, delta L, and radius how much it is decreased here, this much radius is decreased, that is called delta R, which we chosen here. Now what we can call it as means Poissons ratio we need to define. What is meant by Poissons ratio here means longitudinal strain upon lateral strain we are having. So we need to check that first. How much is longitudinal strain? Longitudinal strain. That's nothing but what we can tell along the length. So delta L is increased, this is L. So what we can write it here, delta L upon L, we can write it here, delta L upon L. Now what we need to check means lateral strain we need to check. Lateral strain along the diameter. How much is the increase it is? Delta R decrease in delta R by R we can write it here. That equal to delta R by R, which we can write it here. So now Poissons ratio can be defined as Poissons ratio. It is defined as what means here the ratio of lateral strain to the longitudinal strain. Lateral strain strain divided by longitudinal strain, which you can tell. Longitudinal strain, which we can define here. So that is means what we got it here means that equal to symbol is sigma here. Sigma equal to what we can write it here? Delta R by R divided by delta L by L, which we got it here. This is called what we can call it as Poissons ratio, which we can define here. And what are the Poissons ratio values means? We are having theoretically like this. Theoretically, the values lies between -1 less than or equal to sigma less than or equal to 0.5 lies. So experimentally or practically, if you observe here now, practically, that values lies between what? 0 less than or equal to sigma less than or equal to 0.5, which you can tell here. So here we need to discuss about the relation between sigma, eta, and one more thing, bulk modulus and Young's modulus we need to discuss. Only for competitive also, only come for competitive they'll give you here. JEE or NEET, CET only, they'll ask you these things. We need not to sit and prove these things. You just have to remember. Let me give you the relations. First relation, what you remember means, Young's modulus equal to 2 eta into 1 plus sigma, which we have to know. Second relation, what we have to know here means, Young's modulus equal to 3 beta into 1 minus 2 sigma, we have to know. Third one, what we are going to discuss here means, sigma equal to 3 bulk modulus minus 2 into eta divided by 2 eta plus 6 beta, we have to know. And what is the fourth relation, last relation means 9 by Young's modulus equal to 3 by eta plus 1 by beta. These are the most important formulas for JEE. Every time they used to ask you directly formula only in the questions. Recently JEE 2020 they asked this relation here. JEE 2020 they asked this relation directly. They given in the options here. That's why you have to remember these all formulas are very important formulas, and proofs is not required here. It will take 1 hour time, but you just have to remember that's enough here. More than that not required. Now we are going to discuss about the stress strain curve. Again, choose it. Stress and strain curve. So generally, if you take any random body here, we're having, let me take one spring here. If you apply here load, what will happen? Elongation will come. No, that elongation properties is studied practically, and they given like one curve here. How they given this curve means, this is given curve. We are not going to prove anything here. This is called what means here stress, we can call it as, and this is called what we can call it as strain, which we can call it as here. So stress strain curve we are going to discuss here. In this stress strain curve, what we are having means, so you'll get one curve like this. So this is one point, this is another point, this is another point, this is another point. They given here like this. This point let me choose. Here, this is we named like A, this is we named like B, this is we named like C, this is we named like D, this is we named like E, which we can write it here. So here, up to B, what will happen means stress is directly proportional to strain. Stress is directly proportional to strain. So up to C, what will happen means some elastic properties will be there here. This is called what we can call it as means elastic region, which we can call it as elastic region. So this side, what will happen means regaining is not possible. That's why we can call it as plastic region. So this point is called what means ultimate point. Ultimate point. And this point is called what we can call it means fracture point, which you can tell. Fracture point or breaking point, which you can tell here. So we need to explain This every point step by step we're going to explain here clearly. So first point what we're going to tell means here, from A to B, it follows Hooke's law. Hooke's law, because stress is directly proportional to strain here. Stress is directly proportional to strain, which we can tell here, and it regains its original shape and size. It regains shape and size. We find slope here. No slope, it will use what? Nana? Stress upon strain, which we can get it here. So slope equal to stress upon strain. So that slope doesn't nothing but we can tell like Young's modulus, which we can discuss here. So it is from where to where here? Point A to B, which we can define here. Next, what we can tell here? From B to C. From B to C, material regains its shape, but does not follows Hooke's law. Hooke's law is not valid here. So you are unable to find the what Young's modulus here. Next, point D is called what here? Point D is called ultimate point. Ultimate point where maximum load is applied. Maximum load means maximum stress it can withstand here. Next, what we are having after D, if we apply more load, body will fracture. That's why that point is called what you can call it as here, fracture point, which you can tell here, fracture point. This is how we need to explain the each point clearly. This is stress strain curve, which is learned by practical applications here. Yes, this is for today's class. Please go and revise once again. Thank you.